Hey guys, welcome to this video on the principle of mathematical induction. We're also going to go through proof of divisibility in this video as well. And that's probably it. We'll look at proofs of sequences and series in the next one. So let's start off with the principle of mathematical induction. So if we've got Pn, which represents a proposition which is defined for every integer n, where n's less than or equal to a, and a is just any actual integer. If PA is true, so instead of it being n, we're now doing it being a, and if pk plus 1 is true, whenever pk is true, then pn is true for all of n being greater than or equal to a. So what does this actually mean? Well, if we think about it like a set of dominoes, if we push the first domino over, then the next one's going to fall over, and the next, and the next, and the next. So for k plus 1 domino, so we're talking the k plus 1th domino will topple if the domino before it, in which case this would just be k, topples as well. And then if we give it sufficient time, every domino in this chain would topple over. So we call this the domino effect. What I want you guys to do is to get this written down, and then we're going to look at an actual example of it because it'll make more sense then. So please get this written down, pause the video, get this written down, and then we'll move on. Alright, so welcome back to this example. So the example that we've got here is prove by mathematical induction that x to the power of n minus y to the power of n has a factor x minus y for all positive integers. So if we look at it, let's take it as Pn is going to be equal to x to the power of n minus y to the power of n, and it has a factor right. So x to the power of n minus y to the power of n has a factor of xy for all positive integers of n. So we're now going to prove this by mathematical induction. So if n is going to be equal to 1, that means we're going to have x to the power of 1 minus y to the power of 1, which we know is just equal to x minus y. Therefore, we could say that proposition 1 is true. Now, what we're going to do here is refer back to what we did before and give it as k. So we're going to do proposition k is true. If it's true, let's write it like that. If proposition k is true, then x to the power of k minus y to the power of k has a factor of x minus y. So how are we going to do this? So we're going to go x to the power of k plus 1, remembering that what I mentioned before, if proposition k plus 1 is true, whenever proposition k is true, so we're going to use that part of it. So x to the power of k plus 1 minus y to the power of k plus 1. We could rewrite this as being equal to, and remember we're going to use index laws here, so x to the power of k times x to the power of 1 take y to the power of k times y to the power of 1. Now, let's look at this and see if we can't take out some common factors here or work out exactly what's going on. We could go it being equal to x multiplied by x to the power of k minus y to the power of k plus, oops, let's do the plus over there, x times, far out, x times y to the power of k take y times y to the power of k. Then what we can do is take out the common factor over the right hand side, so over this side, we can take out the common factor of y to the power of k, and what we're going to be left with is x to the power of k minus y to the power of k plus y to the power of k, x minus y. Now we can see that our second term here has the factor of x minus y in it. And we also know that the x to the power of k, we proved that before, if k was equal to 1, or if n was equal to 1, then it's true. So what we can actually say then is that x to the power of k plus 1 take y to the power of k plus 1 has a factor of x minus y whenever x to the power of k minus x to the power of x to the power of k minus y to the power of k has a factor of x minus y. And since our first proposition is true, so P1 is true, and PK plus 1 is true whenever PK is true, our proposition from before, so Pn, this proposition here, must also be true. And this is the process of mathematical induction. So if you guys want to get this example written down, please do. What we're going to do is now talk about proof of divisibility, and that will be the end of this video. So pause the video, get this written down, and then we're going to move on. Alright, so let's talk about proof of divisibility. So what we're going to do here is just prove that 4 to the power of n plus 2 is divisible by 3 for any integer n that is greater than 0 by using the principle of mathematical induction. So whilst this is the proof of divisibility, it could really look at it as another example of mathematical induction. So the way we're going to do this, our first case, so remember we need two cases for this. So case 1, if n is equal to 0, then 4 to the power of 0 plus 2, what does that equal? Well, that just equals 3. And we know that this could really write as 1 times 3. Therefore, our first case of P0 is going to be true. So what we're doing is just looking at simple cases here, and that's going to be the key to any of the proofs. Look at the simplistic cases. What is the most simplistic case that we can do for this? So, if PK, let's look at the second case. If proposition that K, or n is K, is true, that means, or then, 4 to the power of K plus 2 has to equal 3 times A. And a is just going to be an integer that is greater than or equal to 1. What we're going to do now is use the k plus 1 case. So 4 to the power of k plus 1 plus 2, what could be rewritten as 4 to the power of 1 multiplied by 4 to the power of k. Remember that this is just index laws and we can split it up. Plus 2. So what this is going to mean is we could make this equal to 4 multiplied by 3 times a minus 2. Now the reason that we're doing it like this is that we're going to use the proposition of k case. So we know that 4 to the power of k plus 2 is just equal to 3 times a. So we've got this here, the 3a being 4 plus k. We can take 2, I'm going to add 2 to it. What this is going to be equal to is 12a minus 8 plus 2, and just further simplify it down. 12a, take 6, factorize it. And we could take 6 out, but because we're looking at 3, we need to divide, we need to use 3 as our common factor. Now, if that means that if we've got so what this means is if we could see that quite clearly, we could divide, doesn't matter what value of a is in there, we could divide it by 3 and it would still work because we've got this 3 here out the front, and that's what we were aiming to try and get. So try to get that 3 out the front to prove that it's divisible by 3. So that means that 4 to the power of k plus 1 plus 2 is divisible by 3. And we've shown that because 4 to the power of k plus 2 is also divisible by 3. So since our first proposition is true, and what we found for our proposition of k plus 1 is true, whenever our proposition of k is true, that means that our proposition of n is true for all values of n being an integer greater than or equal to 0, where n is greater than or equal to 0. So that's just going through proof of divisibility and a second example of mathematical induction. I'm going to leave the video there, guys. If you've got any questions, please ask. If you've got any comments or feedback, please let me know. As always, thanks for watching, and we'll see you next time.